Welcome to the deep dive. Today, we're unearthing something fundamental, often unseen, about how buildings behave, this really intimate connection between a structure and the ground right underneath it. We're plunging into soil structure interaction, or SSI. You could think of it like the earth itself having a conversation with our buildings, especially when things, start to shake.
Exactly. And for this exploration, we're using a really comprehensive SEMA guide and some other great materials you shared. Our goal here is to sort of distill this complex interaction, make a clear, actionable understanding, really deliver those crucial aha moments without getting too bogged down in, let's say, excessive technical jargon.
Right, because our first image of a building is often, well, pretty solid, isn't it? Rooted to ground that just doesn't move. But the reality is much more nuanced. The soil isn't just a passive base, it's a dynamic participant. It significantly influences how a structure responds to all sorts of forces.
And what's truly fascinating is that it's a two-way street. The soil's flexibility, its movement, can dramatically alter the earthquake forces a building actually feels. It's like a couple bands. The ground influences the building, and the building, in turn, affects the ground. This is quite different from simpler engineering models that just assume a rigid, fixed base. And those simplifications, well, they can sometimes miss critical behaviors, especially when you're dealing with softer ground.
So we're looking at a system where the building, its foundation, and the soil are all interconnected players, always influencing each other. But the key question for us today, I think, is when does this give and take between the ground and the building really matter? When can't we just assume that solid, unmoving foundation?
That's precisely the core of it, yeah.
Yeah.
To really get a handle on SSI, we need to define what it is. At its heart, soil-structure interaction is this dynamic and interdependent dance between a structure, its foundation, and the soil underneath. It's this coupled system where they mutually influence each other's response, especially during dynamic events like earthquakes.
So it's not just the ground shaking the building, it's more complex. The building's reaction actually feeds back into the ground, too.
Precisely. That mutual influence is really what sets SSI apart from those simpler analyses. The fixed space models, they can overlook critical aspects of how a building behaves, particularly with less stable soils or significant ground movement. This whole SSI system involves, well, the superstructure. The bit of the building you see the foundation, which is the interface transferring loads to the soil, and then the soil itself, with its own complex properties that dictate how waves travel and interact.
Okay, so these three components are in constant communication, let's say. What are the main ways they interact? The key physical mechanisms in this sort of underground conversation?
Right, there are several key mechanisms driving this. First, you've got mutual stress transfer. The building puts forces on the foundation, which stresses the soil. But at the same time, the soil's movements push back on the structure. Then there's motion modification. A big, stiff building can actually change how ground motion travels near it. It can filter or even amplify certain seismic waves. And finally, the overall response, how the whole soil foundation structure system behaves together, that's a result of the unique characteristics of each part working in concert.
Got it. A continuous exchange. Forces, motion, back and forth. Now, the FEMA guide and your materials, they use some specific terms. To really understand this, we need to get familiar with the SSI vocabulary, right? Let's start with free field motion. What exactly is that?
Okay. Free field motion, or FFM, is pretty much what it sounds like. It's the ground's movement as it would happen at a specific spot if no building was there. Think of it as the baseline shaking, the raw, undisturbed ground motion itself.
Okay, so the natural ground shaking before any building starts messing with it. Then we have kinematic interaction. What's going on there?
Kinematic interaction describes how a stiff foundation changes that free field motion. Because a large, rigid foundation, well, it can't deform in the same detailed way the soil does. So it tends to average out the ground motion across its base. Imagine like a big raft on choppy water. It rides the bigger waves, but smooths out the tiny ripples. This averaging effect is especially noticeable for higher frequency waves.
Oh, okay.
And you also have waves scattering waves bouncing off the foundation and embedment effects, where buried foundations feel different motions than surface ones. All that contributes to kinematic interaction.
So the foundation acts like a filter, kind of smoothing out some of the shakier parts of the ground movement. Makes sense. Next up is inertial interaction. How's that different?
Right. Inertial interaction kicks in once the building itself starts to sway.
Right.
This is in response to the motion it gets from the foundation, what we call the thin M. The building's mass resists this swaying, generating inertial forces. These forces then travel back down through the foundation and into the soil. This causes more soil deformation and radiates seismic waves away from the foundation.
Ah, okay. So kinematic is more about the ground affecting the foundation initially, and inertial is about the building's movement then affecting the ground. That distinction helps.
Huh.
What about foundation input motion, or FIM?
Foundation input motion, FMM, is essentially the modified ground motion that the base of the structure actually experiences. This is after kinematic interaction has already happened. It's the filtered version of the free field motion that the building really feels right where it connects to the ground.
Right, the ground shaking after the foundation has done its filtering job. Now, soil liquefaction, that sounds pretty dramatic and potentially disastrous.
Oh, it absolutely is. Soil liquefaction is a phenomenon. It can happen in saturated loose soils during strong shaking. The shaking makes the water pressure inside the soil build up really fast. If this pressure gets high enough, the soil particles can actually lose contact with each other. The soil temporarily loses its strength and stiffness, behaving more like a liquid than a solid.
Wow.
Yeah, and this can have catastrophic consequences for foundations. Sinking, tilting, even total collapse.
Definitely sounds like a nightmare scenario for engineers. Okay, moving on. What's the system natural period?
The system natural period is the time it takes for the entire soil structure system, the building and the interacting soil, to complete one full cycle of vibration, back and forth. A key thing about SSI is that the soil's flexibility often makes this natural period longer compared to what it would be if the building were on a perfectly rigid base. Like adding a spring at the bottom, it tends to vibrate more slowly, you see.
So the whole system sways back and forth slower when you factor in the soil's give. Got it. Next, soil stiffness, or shear modulus, G.
Soil stiffness, yeah, often measured as the shear modulus G, is basically how much a soil resists deforming when you apply shear forces trying to make different parts slide past each other. But what's really important here is that the shear modulus of soil isn't constant. It's strain dependent. Its stiffness changes depending on how much it's being deformed by shaking or the building's weight. The more it's pushed and pulled, the, springier or squishier it can become. That's crucial for accurate predictions.
Variable stiffness, okay, that adds another layer of complexity. Then there's damping. I know it relates to energy loss, but how does it break down in the SSI context?
Right, damping. In SSI, we look at it on a few levels. System damping is the overall energy loss in the whole soil structure system. This includes material damping within the soil itself, sometimes called hysteretic damping, which is like internal friction as soil particles rub against each other.
Okay.
Then there's radiation damping, which is pretty unique to SSI. This is energy radiating away from the foundation as seismic waves travel out into the surrounding soil. Think of tossing a pebble in a pond. The ripples carry energy away. Radiation damping is similar for seismic energy around a foundation.
So the soil itself absorbs some energy through friction, and some energy just radiates away like waves. Interesting. Finally, the two main analysis methods, direct method and substructure method. What's the basic difference?
The direct method is, the more comprehensive, all-in-one approach. You create a single integrated computer model that includes the soil, the foundation, and the structure, all analyzed together simultaneously. This often uses advanced techniques like finite element analysis, FEA, or finite difference methods.
So it's modeling the whole shebang interacting in real time, basically. What about the substructure method, then?
The substructure method takes more of a step-by-step approach. It breaks the problem down. First, you analyze the kinematic interaction to figure out the foundation input motion, FEA. Then you characterize the soil foundation system using something called impedance functions. These basically represent the dynamic stiffness and damping the soil provides. These impedance functions are then used in a separate analysis of just the structure. Often the soil's effects are simplified, represented maybe by springs and dashpots attached to the base of the structural model. The FEMA P2091 guide focuses a lot on this method because it's generally more computationally efficient and easier to implement for many engineering jobs, though it might miss some of the really intricate coupling effects the direct method can catch.
Okay, direct is everything at once, complex but complete. Substructure breaks it down, more practical sometimes. Now we have the turns down, let's talk about why SSI actually matters. Why do engineers need to worry about this? Let's start with earthquakes.
Yeah, during earthquakes, SSI can fundamentally change how a building responds. We mentioned period elongation. The building kind of thinks it's vibrating slower because the ground beneath it isn't perfectly rigid. This shift in the building's natural rhythm, it can be good or bad, depending on the earthquake's specific characteristics at that site.
How so?
Well, if the longer period moves the building's response away from the earthquake's dominant frequencies, It could actually reduce the forces. But, as we'll discuss later with Mexico City, if it shifts it towards the ground's dominant frequencies, it can cause resonance and amplify shaking dramatically. SSI also introduces extra damping into the system, remember, from the soil's internal friction and that radiation damping. This increased damping often helps reduce the intensity of the building's vibrations, less energy shaking the building.
So the building shakes at a different frequency, maybe less intensely. Both have big implications for design. What about the foundation itself during a quake?
Oh, absolutely critical. SSI directly impacts things like the soil's bearing capacity. Can it still hold the building up? Also, the potential for the foundation to settle unevenly or slide sideways, or even the risk of the whole building overturning. A proper SSI analysis gives much more realistic estimates of these critical factors under earthquake loads compared to assuming a fixed base.
Which all sounds like it has serious safety consequences.
Exactly. By getting more accurate predictions of the forces and demands, engineers can design safer buildings, implement better risk mitigation. The FEMA guide and your materials also really highlight lessons learned from past earthquakes. Mexico City '85 tragically showed how site amplification and SSI-induced period lengthening can cause catastrophic collapses.
Right.
Kobe '95 exposed the devastation of soil liquefaction and foundation failures directly linked to SSI. And Christchurch in 2011, well, that showed widespread liquefaction impacts across a whole city.
Yeah.
These weren't just theories. They were real-world disasters where SSI was a major player.
So these aren't just abstract concepts. We've seen real tragic consequences when these interactions aren't properly understood or accounted for. But SSI isn't just an earthquake thing, is it? What about non-seismic situations?
That's a great point. Even without earthquakes, SSI can be significant. For instance, very heavy structures on soft, compressible soils. Understanding SSI is vital for predicting settlement, both total and differential, which can cause serious structural issues. It also matters for dynamic loads from, say, heavy machinery in factories. You want to minimize vibrations transmitted around, right? Affecting sensitive equipment or even neighbors.
Makes sense.
For tall, slender structures under wind loads, the foundation's flexibility due to soil interaction can influence the overall dynamic response and stability. And think about offshore structures interacting with the seabed, or even analyzing how digging tunnels or big excavations affects nearby buildings. SSI pops up in many places.
So it's a much broader consideration than just earthquake design.
Okay, let's dig a bit deeper into those interaction components again. Free field motion FFM, the baseline shaking. What else is key about that?
Well, just to reiterate, FFM is the ground motion without the building interfering. Engineers figure this out either through site-specific analysis looking at how soil layers modify bedrock motion, or using code-based design spectra, which are standardized estimates based on region and general soil type. This FFM is the essential starting point, the initial jolt setting the whole SSI system in motion.
Right, the initial seismic wave hitting the site. Now, how does kinematic interaction then change this raw input?
Okay, so kinematic interaction, as we said, is the modification of that FFM caused by the foundation's presence and stiffness. The main things happening are wave scattering, where waves bounce off or bend around the foundation, base slab averaging, where a large rigid foundation averages out spatial variations, especially knocking down high-frequency shaking, and embedment effects.
Yeah, where buried foundations experience different motions than surface ones, because shaking changes with depth and the surrounding soil constrains them. The end result of all this kinematic stuff is the foundation input motion, FIM, the motion the base of the building actually feels.
So the foundation doesn't just copy the ground's movement. It filters it, modifies it based on its size, shape, how deep it is. Okay.
Yeah.
What about inertial interaction in more detail? How does the building's shaking influence the ground?
Inertial interaction, right, that comes from the inertial forces generated by the building as it vibrates. When the building sways, its mass resists accelerating, creating forces at the foundation level. These forces go back into the soil, causing more soil deformation. This deformation leads to radiating seismic waves away from the foundation. That's the radiation damping we talked about, energy dissipating outwards. And importantly, these inertial forces also affect the overall natural period and damping of the entire soil structure system. It's a feedback loop. Building moves, affects soil. Soil responds, affects building's next move.
A true dynamic partnership, then, each influencing the other's dance. Now, under what specific conditions should engineers really be prioritizing a detailed SSI analysis? Are there certain types of structures or soils that make it super critical?
Yes, definitely key scenarios. One of the biggest is heavy, stiff structures on soft, compressible soils. That's where SSI effects are typically maxed out. You can see substantial changes in the system's natural period, sometimes by a really significant percentage.
Okay, heavy on soft is number one.
Conversely, light, flexible structures on very stiff rock-like soils. SSI effects are usually minimal there. Fixed-base assumptions might be perfectly fine for design. However, for critical infrastructure, think bridges, nuclear plants,
Yeah.
tall buildings, a detailed SSI analysis is almost always necessary, regardless of the soil, just because safety and performance are paramount.
Right, can't take chances there.
And industrial facilities, too, especially those with sensitive equipment or hazardous materials, they can really benefit from a thorough SSI analysis to prevent knock-on problems from vibrations or instability.
So heavy on soft, light on stiff, but always check for critical stuff. That's helpful. What are some of the key parameters engineers focus on when they actually do an SSI analysis? What data do they need?
Several parameters are crucial. We've mentioned soil stiffness off of the shear modulus and its damping, the damping ratio. The foundation properties themselves, type, shallow, matte piles, size, shape, embedment, depth, critically important. And of course, the superstructure's dynamic properties, mass distribution, its own stiffness and damping. And finally, understanding the system's natural period, which SSI can change, is a key outcome they're looking for.
And we touched on how different soil types behave. Can you elaborate a bit? How do specific soil and foundation properties sway the SSI effects?
Absolutely. Different soils have vastly different dynamic properties. Soft clays, typically low stiffness, relatively high damping, can lead to significant SSI, big period lengthening. Loose sands, moderate stiffness maybe, but high liquefaction risk under strong shaking. That introduces huge settlement risks and very nonlinear behavior, which complicates things. Dense gravels and sands tend to have a higher stiffness, good drainage, generally more moderate SSI effects, better foundation performance. Bedrock, very high stiffness, very low damping. Usually minimal SSI effects, but might lead to higher frequency responses in the structure itself. And remember, real soil isn't uniform. Layers of different soils create complex wave reflections and refractions, influencing SSI significantly. Foundation embedment, as we said, key role in modifying the motion. And soil damping itself increases with strain, gets better at dissipating energy as it deforms more, which is nonlinear behavior you need to account for.
Okay, the sheer variability of soil is clearly a massive factor. Now, how do engineers actually model this complexity? We mentioned direct and substructure methods. Can you give a bit more detail on how these are applied? This could be a real aha moment for listeners wanting the nuts and bolts.
Sure. The direct method, like we said, models everything soil, foundation, structure as one continuous system in the computer, usually using finite element method, FM, or finite difference method, FDM. These methods break the whole system into a mesh of tiny elements or points and solve the equations of motion for everything together. The big advantage: it can capture the full complexity nonlinear soil, tricky foundation shapes, complex wave stuff. But there's a cost. Direct methods are computationally very intensive, need lots of detailed, accurate soil data, which can be expensive and hard to get.
So incredibly powerful but demanding. What about the more common substructure method? How does that work in practice?
The substructure method simplifies things by breaking it down. Step 1. Analyze kinematic interaction to get the foundation input motion, FIM, how the foundation modifies the free field motion. This often involves looking at wave scattering and averaging. Step 2. Characterize the soil foundation system with impedance functions. These describe the soil's resistance, stiffness, and damping to the foundation moving, usually varying with frequency.
Impedance functions.
Right. Finally, step 3. Incorporate these impedance functions into the structural model, often represented as springs and dashpots attached to the structure's base. Then you analyze the structure's response to the FEM, considering the support from those springs and dashpots. FEMA P2091 gives detailed procedures for this, using simplified soil representations. Makes it more accessible for routine design, even if it doesn't capture every single nuance like the direct method might.
Springs and dashpots at the base. Yeah, that makes the soil's influence much easier to picture. Now, in a real-world SSI analysis, what specific factors need close attention? Like the difference between free field motion and what the foundation feels seems huge.
Absolutely crucial difference. Kinematic interaction means the FSIM can be significantly different from the FFM. Engineers have to carefully consider these effects, averaging high frequencies, modified motions, due to embedment to get the actual seismic demand at the base. Then, they need to account for inertial interaction, how the building's response feeds back into the soil, affecting period and damping. And for buildings with basements, Properly modeling the lateral resistance from basement walls interacting with soil is vital. That can really change behavior compared to a no-basement structure.
Basements add a whole new dimension, literally. Okay, what key advice would you give engineers doing an SSI analysis to ensure they get reliable results?
Several critical things.
Yeah.
First, know when SSI is likely significant to use those screening rules of thumb. Second, invest in good site characterization. Reliable soil data is fundamental. Third, pick the right modeling approach and software for the job and your expertise. Develop realistic, well-validated models. Pay attention to soil, foundation, and the interface.
Makes sense.
Define the seismic input accurately, preferably site-specific hazard analysis. Account for soil nonlinearity, especially under strong shaking. Do sensitivity studies. Check how uncertainties in soil properties affect results. And always apply sound engineering judgment. These tools aid thinking, they don't replace it. Foster collaboration between structural and geotechnical engineers. And document everything meticulously. Assumptions, results, the lot.
Solid, practical advice. And for listeners wanting to explore more, what resources are out there?
Oh, there's a wealth of information. Powerful software like OpenSeas, ABQUS, ANSI, OSSIES, Plaxis, SASI, Fleesh. Building codes like ASC7 in the US, Eurocode 8 in Europe have SSI provisions. Academic literature is vast journals, conferences. Case studies from past earthquakes offer invaluable real-world lessons. And practical guides like FEMA P2091 provide accessible methods for engineers.
Lots to dig into. Let's circle back and recap those key SSI phenomena, really highlighting why they matter. Period lengthening, how does that practically impact a building in a quake?
Right, period lengthening.
Right.
Increase in vibration period due to soil flexibility. For buildings on soft soils, it can be substantial. The practical consequence: the building sways slower than on a rigid base. Now, whether that's good or bad depends on the earthquake's frequency content. If the longer period shifts the building away from the earthquake's dominant frequencies, forces can actually reduce. But if the soil itself has a natural period close to this lengthened building period, like in Mexico City, you get resonance, amplified shaking, disaster.
A double-edged sword, then. Potentially helpful, potentially very dangerous. What about foundation damping? How does that energy loss typically affect the response?
Foundation damping, both hysteretic, soil friction, and radiation, waves radiating away, generally increases the overall energy dissipation. More damping usually means reduced peak vibrations during an earthquake, lower forces, potentially less damage. It acts like a shock absorber.
And base slab averaging for large foundations, the practical benefit there?
Base slab averaging, yeah. Because a big, rigid foundation smooths out complex ground motion, it effectively filters out high-frequency components. This is particularly good for short-period structures, reducing the impact of those sharp high-frequency jolts. It rides the bigger waves, not every little ripple.
And finally, embedment effects burying the foundation deeper. How does that usually influence the motion the building feels?
Generally, embedding a foundation tends to reduce the motion amplitude it experiences compared to a surface foundation. It affects both the intensity and frequency content transmitted up. It can be particularly helpful in reducing rocking motions and overall seismic demands.
All these really show the ground isn't just passive support. Now, you mentioned a rule of thumb for assessing inertial SSI significance. Can you remind us of that?
Yes, the quick check. It involves a ratio. Building's fundamental period, T, times its effective height, divided by the soil's effective shear wave velocity, VZs, times a represented base dimension B. If this ratio T-half, the SB, is significantly bigger than about 0.1, it signals that inertial SSI effects are likely important enough to need a closer look. Crucially, use an effective Vs relevant to the interaction depth and strain levels, which might not be the same as the standard site classification VS30.
Okay, a simple calculation for an initial flag. And when engineers do account for SSI, what's the typical impact on the calculated seismic forces?
Generally speaking, proper SSI analysis, especially when inertial effects matter, often leads to reduced calculated seismic forces, particularly for stiffer, shorter period buildings and higher vibration modes in tall ones. This happens because of the increased damping and the potential period lengthening, moving away from peak earthquake frequencies. But, and this is a big but, building codes usually limit how much you can reduce design forces due to SSI. They build in conservatism for uncertainties.
Right, you can't just assume the ground will always save you money on steel or concrete. Now, we absolutely have to revisit the Mexico City earthquake, 1985. Such a powerful, tragic reminder that SSI isn't always beneficial. What went so wrong there?
Yeah, Mexico City is the stark counterexample. The key was the unique geology deep incredibly soft lakebed clays. These clays have very low shear wave velocity and amplify seismic waves dramatically, especially in a specific long period range, around 1 to 2 seconds.
Okay.
Mid-rise buildings, maybe 10 to 20 stories, had natural periods that, when lengthened by SSI due to the soft soil, shifted right into this amplified range. This caused resonance. The building's natural sway matched the ground's amplified shaking frequency. The result was a massive amplification of building vibrations, widespread structural failures, catastrophic collapses. It starkly shows SSI effects are highly site-specific, depends critically on the interplay between soil properties, building properties, and the earthquake's frequencies. A powerful, tragic lesson that SSI can be profoundly negative.
A crucial and very sobering counterpoint indeed. So as we wrap up this duck dive, what's the single most important message you want listeners to take away about soil-structure interaction?
The fundamental takeaway is this. The ground isn't just a static base. It's an active, complex partner in how structures respond to dynamic events, especially earthquakes. Understanding and properly accounting for SSI is just essential for designing safer, more resilient, more effective buildings. Period.
And hopefully we've sparked some of those aha moments for you, our listener, from the maybe counterintuitive benefits SSI can sometimes offer on soft soils to the devastating consequences it unleashed in places like Mexico City when things aligned badly.
Absolutely. It really encourages us all to think more holistically about the built environment and all the dynamic forces happening right beneath our feet.
So here's a final thought to chew on. As our ability to characterize soil improves, as our models get more sophisticated, maybe even incorporating real-time data, how might these advances change structural design? Could we engineer buildings that are even more tailored, maybe even adaptive, truly understanding and responding to their relationship with the ground through SSI?
That's a fascinating question. I think those advancements will absolutely pave the way for more refined designs, potentially even adaptive structural systems that better handle SSI complexities. It could really lead to a new era of safer, more resilient infrastructure, especially in seismic zones, but really everywhere.
Indeed. Well, thank you for joining us for this deep dive into the fascinating world beneath our feet. Until our next exploration, keep questioning the foundations of the world around you.